So we are going to cover chapter 1 here, and so one of the first things that we're going to talk about is why we even study any of this, okay? So some of you had said that you don't have as much experience in electronics, and some of you have never worked with electronics or circuits before at all. And so one of the major things that you're going to learn in this class is, you're not going to be able to like start your own little business. But if you have something that's not working, unless it's software based, like your smartphone, you're not going to be able to fix your smartphone. But if you have some other kind of device that's not working the way you think it's supposed to, then you will feel more comfortable taking it apart and just looking and seeing what you can see. Sometimes it's still too complicated, but I've had students who have taken their TVs apart and noticed that there was a diode or something that was burned out, and they replaced it and the TV worked fine again. So, instead of throwing away a $400 or $500 TV, being able to fix it and then going about your day. So there are little things like that you'll feel more comfortable doing. You may even feel more comfortable if you just want to check an outlet to see if there's 120 volts there. I know that that's one of the first things that I felt comfortable doing after taking this class 20 some years ago. And you'll just be safer around electrical devices, period, right? And our whole world is electrical and digital now, right? So, if you look at a circuit board and you find burnt resistors or bad wiring or bad capacitors or blown coils or something, you can look in that stuff and go, oh, if I just unsolder that and put a new one in, then I can fix my device, whatever it is. But if you are a ECET student, there's also another benefit of this class is that you're going to use it in almost every other class that you take. Okay, you're not going to be doing nodal analysis like in 223, I don't think, but you will have, you'll have a better understanding of how electricity moves through a circuit. Okay, and that's the main point is that you understand how electrons move, how circuits work. How to measure things, how to calculate things, and so this is very much a stepping stone for everything else you do in ECET. And from my list here, we are very, very heavily ECET slanted in this class. Okay, so normally sometimes I get about 50-50, 50% MET, 50% ECET, but this time I have very few MET students. So, yeah. So, almost all of you will use this information in a future class. You will use the same techniques, you'll just use different components, okay? Some of this stuff is like if we were in person. So, the way that all electrical devices work, if you just wanted to look at the 30,000-foot view, is that it says electrical things work by sending charged particles around a closed loop or a circuit. So we control the flow of those particles, and sometimes we don't need as many of them. Sometimes we need more of them, and we do that with our lighting, our heating and cooling, all of the motors and clocks, and now our smartphones. Everything runs off electricity, right? So some of the things that we are measuring in this class, and we are looking to measure, is the voltage and also the current. Now we also do resistance measurements and resistance values and things like that, but the two major measurement values that we deal with in this class are voltage and current. Now we'll also calculate a lot of other things like power and things like that, and time constants, but everything is all referenced on voltage and current, right? So voltage, the amount of power moving each electron, and we measure that and calculate in volts and have our formulas in volts. And then we also have a current, which is the movement of those particles, right? It's the amount of flow in amps. Okay, so we're going to find that current is not something that you can, like volts. I say how many electrons are there, right? Per whatever, right? So I have a battery that's at 12 volts, and it's got X amount of capacitance in it, and so it can release a certain amount of power, okay? But current is a measurement of flow, and so if you've done any work in physics before, you know that when you have a rate of something, so for instance, if I walk from point A to point B, that distance is my displacement, okay? And if you take the derivative of that displacement, you're saying, okay, what's the rate of speed, essentially, that you're getting from point A to point B? How fast is that happening? Well, I'm doing it, 8 meters per second or 2 meters per second, right? It qualifies how quickly you get from point A to point B. So current is similar. I don't want to say it's the exact same thing, but it's very, very similar, okay? It's how quickly and, to some degree, how much of those electrons are flowing around a circuit and how quickly that's happening, okay? So think about current just like you would water current or air current, okay? And we'll get more into that when we talk about chapter 2. So, audio, visual, radio, pretty much everything. Like I said, even our TV's not even analog anymore. Our TVs are all digital because we all go through, either Ethernet to watch. I do have a couple of friends that still have antenna TVs, but even those antennas pick up a digital signal now. There is no more analog, right? So, digital is outside the scope of this class, but prior to, 20 years ago, everything was analog, and so radio frequency and all that good stuff played a bigger part in how some of this stuff gets transmitted. It still gets transmitted, to satellites and things like that, but the whole network is completely different than it was 20 or 30 years ago. Okay, so some of the things that we use, right? If you work in any manufacturing facility, you're going to have temperature gauges, you're going to have pressure gauges, you're going to have lighting all throughout the place, and then you can get into what kind of lighting you have and what power is required to start those lights up if you have high pressure sodium. Like if you've ever played baseball before at night, or if you played tennis at night, and like maybe in your high school that's what you did. When they turn those high pressure sodium lights on, they don't just instantly come on like the filament lights do in our homes, okay? It takes time for those things to warm up and to get up to temperature, and then they can display the light that they're supposed to display. But it takes some time to light up like that, okay? And so control systems, we also, I talked earlier a little bit about PLCs and about automating things and getting people off the manufacturing line and off the assembly line. Well, the assembly line is a little bit more difficult because as humans, our fingers and our hands are very, very useful tools when it comes to assembling things, okay? But we've got some machines that can assemble as well. There are some things that are built entirely by robots from start to finish, okay? If you ever watch there's one I always show in my PLC class, the BMW, excuse me, I believe it's the i3. It's the smallest electric vehicle that they make. If you watch that, it's about 40 minutes or so. If you watch that, there are very few places in that entire process where a human even makes contact with any of the manufacturing stuff. And even when they do make contact, it's like, okay, I'm going to move this piece from over here to this other presser machine, and then I'm going to push a button that starts it. Okay, so it's still, we're still not doing a whole lot in the manufacturing process. Most of that has gone to these control systems that use cameras and pressure and temperature and other measurement techniques to control the process. Okay, so maybe you've worked in a facility like that. I don't know. I did not work in a facility like that, but I went to about almost 400 different locations in my 4 years, and that's all over the state of Indiana, some in Kentucky, some in Ohio, only one in Illinois, and one up in Michigan. We took care of the Harmon Becker plant up in Farmington Hills, Michigan. But other than that, all the stuff that I went to was in Indiana. So I saw all kinds of manufacturing facilities that did all these different things and saw how PLCs were at the heart of almost all of it. And so, PLCs is a specific, outlet of the EET program. But it's all still based on the fact that all that stuff has to be electrically powered, right? So how are you going to make sure that your PLC is safe? What circuit is it on? Does it have enough protection? Does it have overload protection? And, what about the facility in general. If you work out at Rolls-Royce, which used to be, well, it's still Allison Transmission out there, but I don't know if they still do this, but they made aircraft engines out there. So the devices that they're using are not running off 120. Some of those devices are running off of, tens of thousands of volts. So whereas you have 240 service, 240 volt service into your residential home that you can then have down to 120, but that's what a standard residential home has service as, 240 volts. So if you work in one of those big facilities, you may have 300,000 volt service, and then you distribute that throughout your facility. But some of those pieces of equipment require a ton of power to operate on. This stuff is used everywhere. Everywhere we do business, essentially. Okay. So here are some of the components. One of the things we're going to talk about is the resistors, and their entire existence is to limit the amount of current in a circuit. Okay, so you might think to yourself, why would you want to do that? Why wouldn't you just hook a device right up to the voltage? Well, if you do that, the only resistance is in the wire itself, and so you're going to have a very, very high current that may damage your load. Okay, more than likely it's going to damage your loads. Think about an LED for a second. So your smartphone probably has a little blinking LED on it that probably runs, 24 milliwatts roughly of power. I know you guys don't really know what that means yet, but it drops about 2.2 volts, and it has an operating current range of 10 milliamps, or 10 thousandths of an amp, to 20 thousandths of an amp. So if you put 1 amp through an LED, you're going to blow it. So, depending on what load you have, you want to limit the current to the proper operating range. So that's why we use resistors. Okay. Capacitors are able to store electrical charge and release it very, very quickly, much more quickly than a standard battery, because they don't have an internal series resistance, which we'll talk about in chapter 13. But so capacitors have the ability to store electrons, which we'll talk about, and they can release those electrons very, very quickly. So when it comes to replacing something like this, especially if they're bigger, like if you were to ever take apart your not your laptop, but your PC, and you have to you see that there's a capacitor blown in your power supply. I would never get inside that power supply myself, because some of those capacitors are charged to kilovolts. Okay, that's how much power that they can retain. And so if you accidentally touch both those leads on your skin and you've got kilovolts of power, you're going to have a bad day. Okay, so capacitors are a little bit more dangerous. The size that we work with are not dangerous, because they will only hold a certain amount of volts, and we don't, the most voltage we're going to work with in here is 9 volts, right? Because that's how we're going to power our circuits, with a little 9-volt battery. So, you still want to be respectful of the electricity, but the capacitors that we use are nowhere near what like what you might find in one of the old TVs, the old console TVs. Some of those had capacitors that were charged to kilovolts as well. So we'll talk more about that in chapter 13, I believe it is, and then also inductors, chapter 11. And so inductors is another component that we use, and they're also used to store energy. So we store energy in an electric field with capacitors. We let electrons assemble on one side, one terminal here. And with inductors, it stores it in an electromagnetic field, because an inductor is nothing more than a coil of wire. Okay, and so we'll talk about magnetism and how when you coil the wire together like that, you sum all of the electromagnetic waves together to get a stronger energy field. Okay, and so that has to have an active connection on it. The capacitors will store electricity if you remove power from the circuit. Okay, but like I said, all the nuanced stuff about capacitors and inductors we'll talk in the last third of the class. So that's a long time from now. Okay. Transformers is a variant on the inductor. Essentially, it uses 2 inductors side by side, coiled together. And most of the time, they're used to either step voltage up. So you may have a transformer. Well, I know you have a transformer if you have a power supply on your phone, the little box, or if you have a laptop, that little square brick, okay? That square brick is taking the AC voltage, the sine wave voltage out of the wall and converting it into a stable, constant DC signal, okay? And so most of the time you're stepping down, but you could also step up, and you could also have a unity where it's a 1-to-1, all right? So, most of the time they're used for increasing and decreasing AC voltages. Again, last third of the class, but that's another component that we're going to talk about. We're also going to discuss some of the semiconductors. Now, transistors you will get in 121. That's with Professor Atkins, okay? But we will cover the diodes in this class. We'll cover light-emitting diodes, LEDs. We will cover standard silicon diodes. We will touch on germanium diodes and also Zener diodes. So we will do a lot of work with diodes in this class, but we will not get to the transistors, okay? But one big thing that they're used for is an electronic switch, okay? And the transistors and diodes both work as switches, and they also work as protection, and we'll talk about why that is. ICs are also semiconductors because they're usually silicon-based, and if you take 112 or 122, both those classes, we talk about these an awful lot, okay? But those are more for digital. Two of the instruments that we're going to use in this class, instead of using a variable DC power supply like this one that you see, we will use a 9-volt battery, which is also a DC power supply. Okay, that's not how we talk about a 9-volt battery. We just talk about it as, this device needs a 9-volt, and this one needs a AA, and this one needs a AAA. So I'll ask this in the comments here. What is the voltage of a AA or AAA or C or D battery? I didn't know this until I started taking this class 20 years ago. So what's the voltage of a AA or AAA or a C or a D battery? Does anybody know? I'll put that in the comments, and if you have the answer, go ahead and type it in. Okay, so instead of using a nice digital display DC power supply, which is what we have in the lab, you will use a 9-volt battery. Okay, no big deal. You will also use something that looks very similar to this yellow DMM, but this is called a digital multimeter. Okay, now before they had the DMM and before it was really, really popular, they used to use analog devices, and you would have to know what range of voltage and what range of current that you wanted to measure, because you had to go get a separate measurement device for each range, right? So what the DMM does is it makes it all digital, and so you have a knob on here that will, and I go over how to use the Mass Tech, by the way, so you don't have to take a bunch of notes on this part. So it's got one of the knobs will be for voltage, and one of them will be for, AC voltage. The other one will be for DC voltage. The other one will be for DC current, AC current. We even have one that does capacitors, right? That the Mass Tech will do capacitance. It will also do thermocouples. It actually comes with a thermocouple. So the DMMs of today do 10 different functional operations, and they do it all in one single package. And what is it, $30, $35, something like that? Something like that in 1970 would probably be $400 or $500. So, and you can buy them in different categories. The one that we buy is a Cat 3, and so we don't go into the safety of multimeters, but Cat 3 is almost as good. It is pretty much industry standard. But if you really do a lot of higher voltage, then they recommend the Cat 4, all right? And so Fluke is definitely, in my opinion, the leader in safety in DMMs and measurement devices. And when I worked at the calibration lab, we had all Fluke equipment, unless we just couldn't get a Fluke piece to be our what would you call it, the lab calibration standard. We call them calibration standards. So, when you would send your device in and, mine has to be 4 times as better, nobody did it better than Fluke when it came to electronics. And so, all of our stuff was Fluke, but I did, who knows how many brands are out there. These days, there's even more brands because the way that our manufacturing works now is typically there's a few giant facilities in China that do the manufacturing of the base product, and then there's another, who knows how many Chinese companies that essentially all take the same board and then they put their cosmetics on it. But at the heart of it, they're all essentially the same device, right? And I find this in woodworking too. So, there's a couple of places in China that mass produce planers, electric planers. And so one company sells to Porter Cable, which is what I have. And then another company will sell to Delta, and another company will sell to Wen, and another company will sell to the Harbor Freight brand, which I can't think of. I think it's, I don't know if that's the Chicago Electric one or not. But all of those companies have the same base motors and components, and then they put their colors and their cosmetics on it and then sell it. And they're, if you look at all of those different planers, they're all like the same price because they all have the same manufacturing process. Just, which color do you like better, essentially? But if you tried to do that same thing here, they would probably cost twice as much. But they just mass produce these things because that's also where all the semiconductor, most of the semiconductors are created also. And so, you have a lot of this foundational manufacturing stuff that's manufactured there anyway, and so it all gets assembled, and then a lot of it gets cosmetics put on when it gets sold. So we will be working with a power supply and a multimeter. Now, when it comes to the function generator and the oscope, we will be doing that virtually through multisim. Okay, and the function generator essentially will create an AC signal. And it could be an AC sine wave, it could be a square wave, it could be a triangle wave, it could be a sawtooth wave. So that's what a function generator does. It allows you to choose the amplitude or the voltage of the signal, and it also allows you to choose the type of signal and then also the frequency. So you could have a sine wave at 100 hertz and 4 volts peak voltage. Okay, so that's the kind of thing that you can do with a function generator. So it's kind of like the AC power supply, if you will. So here's the DC power supply, and we haven't even talked about what AC versus DC means, but for the first 2/3 of the class, we'll be using a DC power supply. For the last third, we will do some work with the function generator, right? And then, so, if we were to use an oscilloscope, which is the other device that we used, it wouldn't make sense for us to use the oscilloscope to look at a DC signal because a DC signal is straight and flat and it doesn't change. And so that would be very uninteresting to look at on an oscilloscope, to just see a straight flat line. But when you deal with something that's repeating and it is alternating, like a sine wave, that becomes very interesting to look at because now I can see, if I'm looking at the voltage on a resistor versus the voltage on an inductor, those two things are going to be out of phase, and I can measure how much they're out of phase, and I can see, how far ahead one signal precedes the other, because that's what happens when you get into the AC and start adding capacitors and inductors. So that kind of stuff is very interesting to look at on an oscilloscope, but because we don't cover AC till the last third, that goes along with the function generator. So these two things are typically used for the AC circuits, and then these are used for DC circuits. Now, the multimeter has an AC voltage and an AC current measurement on it. We just don't have a way to, I guess I could rig something up that you plug into your wall, but then if you don't rig it up right and start a fire, then it's my fault. So we're just going to do the AC portion virtual, okay? So, one of the first things we should say about this is that, excuse me, that electricity can kill you, right? If you just want to be blunt about it. And in some places, they use electricity, as capital punishment. So it's very, very dangerous. And, around 2 milliamps would shock you. And it only takes 50 to 100 milliamps to kill you. Okay? And so you just have to be very, very careful. And so it says 120 volts can put 12 milliamps through you. A wall socket has plus or minus 170 volts. And so you've probably always heard either 110 or 120 out of the wall. That's volts RMS. You know, the actual signal that's coming out of the wall is 340 volts peak to peak, which means it has 170 volts positive peak and negative 170 volts negative peak or minimum, okay? So it's not just 120, it's 170, all right? And so that's bad news. If you've ever gotten shocked out of a 120 volt outlet before, it's no fun, all right? It's happened to me multiple times. And the other reason another thing we're going to talk about with safety is water. And anything that's got water in it typically is going to be a good conductor for electricity. And the reason why is that it lowers the overall resistance. So if your body is wet, you will have less resistance. And we're actually going to go through that procedure with your DMM. So one of the measurements that you're going to be asked to do is take the multimeter in your hands and have one probe in each with your forefinger and your thumb, and you're going to measure your body's overall resistance. And then you're going to squeeze those probes a little bit tighter to make a better seal on there and see how that changes the resistance. And then you're going to lick your fingers and do the same thing. When you lick your fingers, you're facilitating the signal to transfer from the probe to your finger, and you're going to get a lower overall resistance, okay? So that is bad news if you're talking about a fully powered circuit, because when you reduce the resistance, by default, you will increase the current, and that's what becomes deadly. So don't have any water around you. You're gonna see this safety stuff 3 times at least. You'll see it in the quiz. You will see it in the lab. Well, okay, you might see it 4 times. You'll see it in the quiz. You'll see it in the lab. Okay, and then you'll also see it in the first test. And I may even ask you about it again on the final. That's how important it is, because we have an industry advisory board that comes and has meetings with us, and we say, hey, what do you want us to focus on? And one of the things they always tell us is you have to start focusing more and more on safety, so that we don't have people coming in here making, even with training that they get, they don't have a respect for it, and then they get in trouble, okay? So don't work alone. Have a buddy with you. Well, that's kind of impossible right now, so your buddy is me virtually, I suppose. But like I said, we're only going to be using 9-volt batteries, so I'm very comfortable with every connection you're going to make. Even if you happen to short circuit, you're not going to create an explosion, okay? So I don't want you to feel fearful, because we're only working with a 9-volt battery. And that 9-volt battery has protections inside of it. Same thing for a AA, same thing for a AAA. And, yep, so everybody, I just came back here. So, yep, 1.5 volts. So, okay. So Joseph, if you need to leave, that's not a big deal, okay? Yeah, so Austin answered that for you. All right. So yes, 1.5 volts. So you may not have known that before. So the size of a AA versus a AAA is pretty significant. But then think about a AAA versus a D battery. The D battery is what I put in. We had this electronic swing for our daughter that took 4 D batteries, and it would only last 2 or 3 hours. So it got very expensive to run it. So yes, a D battery, if you put your multimeter on it, will measure 1.5 volts. And if you take that same multimeter in the same range and put it on a AAA battery, you have 1.5 volts, okay? The difference, obviously, is the fact that it's got a whole lot more electrons that it can disperse at that voltage, and so it can create a higher power. If you try to draw too much amperage out of a AA battery, it's going to heat up and it won't function properly. So if you need to draw more power, that's where you would use the bigger, either the C or the D batteries, okay? So AAA batteries are great if you need to generate a 10 to 20 milliamp signal on your LED on your remote control, right? That it can do that no problem, because it's typically you just hit it and then you're done. You have the signal go for a second and then it's done. You wouldn't want to try to power a baby swing with AAA batteries. It would take, geez, who knows how many it would take, but more than more than just a few, and you'd have to wire them all in parallel too. But anyway, yes, 1.5 volts is the correct answer. So, don't wear any chains or big rings or anything like that. Like I have gotten in the habit, well, I don't have to worry about it anymore, but when I was at school, I would leave my wedding band in my office. That way I didn't have any possibility of that metal touching a circuit. So I would even go as far as, it doesn't even have to be a big ring, but if you could get your wedding ring on and off, I suggest just being as safe as possible. We don't have to worry about any of this stuff because you're going to be plugging everything in at your home, okay? So let's talk about atomic theory, the structure of an atom. And so for some of you, this may be review, which is great. For some of you, this may be the first time you've ever talked about the structure of an atom. And you've probably heard the term proton, neutron, electron, and nucleus, and atomic bombs. And so you've probably heard those terms before. So, this is not a physics class, and this is not a chemistry class where we're going to talk a whole lot about this, but you need to understand how the different types of materials work. And I mean the electrons, how they move in a conductor versus how they don't move in an insulator, versus how they might move in a semiconductor. So we need to know how the structure of an atom works to understand how these electrons are moving from, if we have copper wire, how is it moving from a copper electron, a copper atom to another copper atom, okay? So the basic structure, the Bohr model at least, there are other different models about, what the ways to visualize an atom, right? The true three-dimensional model would work a little bit better because, it doesn't just do a nice two-dimensional, it just rotates like this. You could have them rotating in different directions. Like if I'm trying to pull my cursor towards me, obviously that's not working, but they're all rotating around this nucleus, right? And they rotate in these rings, in these shells, okay? And we're going to focus mostly on this outer shell, okay? And so for some of you who have taken physics before, I'm typing this in the chat, what is the name of the outermost shell of an atom? So that's going to determine whether something is a conductor versus an insulator versus a semiconductor. So what is the name of that outermost shell of electrons? You can go ahead and type it in. So, Alex, yes, the electron is what rotates in those shells, but what is that outermost shell? Yes, valence, that's what I was looking for. So, the valence shell is this outer shell here, okay, and that's what we're going to concentrate on. So, if I had my studio, when I get my studio built, and it should be in the next day or two when I have it all finalized, because I've got 90% of it done, but I built a frame around my, my periodic table of elements. And so if you know anything about how the periodic table is organized, on the left-hand side you have everything that's got, excuse me, mercy, everything has got one electron in that outer valence shell, okay? The valence shell itself will only hold up to 8 electrons. So if you have 8 electrons, it's full. Those are our noble gases like helium and xenon and things like that. Those are over on the right-hand side of the periodic table. So everything on the left-hand side that's got from 1 to 3, right, it's got potentially 5 to 7 other spaces where free electrons can easily pass. So part of the reason why we use copper is because it only has one electron in that outer valence shell. That means there's 7 spots for free electrons to move. Okay, and it makes it very, very easy for free electrons to move from atom to atom and make their way to the end of the circuit. Okay, once you start clouding, or once you start populating that outer shell, as you move to the right of the periodic table, you come to where we have 4 in the middle. Okay, now, this carbon atom, is the basis of a lot of the semiconductors, right? Silicon is the same way, germanium is the same way, and so there is room for the electrons to pass. It's just not as easy, and so you have to meet certain conditions before something like this will conduct electricity. Okay, now we have to have something. Well, I guess we don't have to, but the way that we create our wiring is that we have the center conductor, and then we have an insulator that wraps around it. So that way, if we have something turned on and we grab the cord, we don't shock ourselves, right? So we have an insulator that does not allow the electrons to pass very easily because they have anywhere from 6 to 8 in this outer shell. Those make great insulators because it's almost like a balloon, okay? When I think about a copper atom and all this space here, it's like a balloon that, for lack of a better term, is flaccid, right? It hasn't been pumped up yet. So when you take that first big breath and that balloon it's flaccid, right? You blow into it and it's very, very easy to empty your lungs in, right? Then the second time you blow, maybe it's a little bit harder, but by the time you get to that third or fourth blow, depending on how big the balloon is, not only do you have to put air into the balloon, you also have to equalize the pressure and the flow that's trying to come back out, because if you let the balloon go, what happens? It evacuates itself, right? Because air pressure is 14.1 psi, and if you start blowing that up, you're pressurizing the inside of that, and it wants to release itself, okay? So once you get to about 80% full, 90% full, and you try to put that last little bit in, you have to overcome not only what's already in there, right? And then try to add something on top of that. So you have to match the pressure in there and then add some to it to get any more in. It becomes very, very difficult. So that's the way I think about insulators, is that it's pretty full. It's almost impossible to get anything else passed through there, okay, without going deeper into the structure of an atom. I mean, that's the basic idea that I want you to take from this, okay? So again, electrons, very, very small. Protons, they're actually almost 2,000 times heavier, but when we're talking about something that's this small anyway, that I don't even know the prefix for, and we have to use scientific notation here, it's very, very, very small. And even though this is 2,000 times heavier, 2,000 times this is still extremely small, okay? So again, the valence band is the outermost shell, and a valence electron is an electron that you find in that valence shell. And it's full when it has 8 electrons, and an atom with a full valence shell is said to be stable, right? So that's our noble gases, right? But you can also do some chemistry, like potassium chloride. You can have one that's got 3 and another one that's got 5, and then, when you combine them together, the 3 latch onto the spot where there's 3 available in that other shell, and you can make a nice stable connection, right? So that's mostly what chemistry is trying to balance that connection. Okay, so here's a little, I would say this, okay, and I would say 4 to 5 here, okay. So if the conductor has 1 to 3 valence electrons, that means electrons can freely move because there's plenty of space. If it's an insulator, it's essentially full, and it has very few free electrons that can pass, if any at all. Now, if you get too many, and if it's too hot, you could certainly break down the insulation, and then you have trouble. But, wood, plastic, glass, ceramic, all those things are great insulators. Okay, semiconductors right in the middle. So yes, they will conduct. However, you do have to meet certain requirements. And typically with a silicon diode, that means at least 0.7 volts has to be dropped across it for it to operate and conduct current. For a germanium transistor, it's anywhere from like 0.2, 0.3, depends on what type you get. We do not use germanium transistors anymore. And the reason why is because, like, let's say you were to take your smartphone and you went on vacation to Alaska. It's very, very cold, sub-zero temperatures up there. You want your phone to be able to work there, and then let's say you come back home and then you go to the gym and get in the sauna where it's 180 degrees, and you want your phone to work there as well. Well, if you had germanium diodes and germanium transistors, it probably wouldn't work in either place because it needs a stable, more stable conditions to operate in, all right? So silicon is dead on. Silicon is one of the most stable elements that we have. Actually the silicon wavelength is now the SI unit for length. It used to be this piece of wood that they had under triple lock and key and temperature and humidity environment in France. And so that was like the ultimate reference for what a meter is. So that's my world right there, where you talk about what's the standard for, all of the measurement tools that we have in the world. Who decided what a meter is, right? Well, they have a piece of wood that's under triple lock and key in France that they decided that's what a meter was, right? A meter is just an arbitrary unit of measurement that we decided, okay, this from here to here, that's a meter. And so that's what all of our measurements are going to be based off of. So what they found is that, over time, they have very, very sensitive dimensional measurements that can measure out to the billionths. And they were noticing that this thing, I can't remember if it was growing or shrinking. I think it was growing. But it was actually changing enough that they said, okay, we need to figure out a different way to come up with this. And so they used the silicon wavelength to be the now the SI unit. And it's stable. It's never going to change. Okay? But for, centuries, that piece of wood that was under lock and key was the official meter in the entire world, right? So you might have thought to yourself, if you go buy a ruler, okay, well, where did that ruler, or a steel rule, where did that get made? How do they know what an inch is? How do you know if this is accurate or not, okay? Sometimes you take a tape measure, if you've ever done any type of construction, if you take one brand of tape measure and measure it against another tape measure, sometimes they're just a little bit off. And so which one is the more appropriate one to use? Well, for most things that we do, it's not, you don't need that type of accuracy. If you when I do my woodworking, if I use the same measurement tape for the whole project, and I know they all reference off that same measurement tape, it doesn't really matter if it's, 9 inches or 9 inches and a quarter or whatever. It just, the two pieces of wood have to match up. And so if I'm using different measurement tapes, believe it or not, I could get some slightly different lengths, off by a 16th, off by an 1/8. You'd be surprised how much variance there is in measurement tools. It really opened my eyes to work at that lab because a steel rule is still subject to temperature over time. And so if it's always in a hot environment and then it gets sent to our lab, and our lab was kept at, our dimensional lab was 68 degrees, I think. It was cold enough to where our technicians had to wear a jacket in there, and that metal will shrink back down, and so it could affect when you're expanding it and contracting it and expanding it and contracting it. Sometimes that can actually throw the steel rule off enough to where it fails a calibration. So in that regard, plastic is more stable. If you've ever had a plastic ruler, now they have very, very typically fat tick marks, which reduces the accuracy. But anyway, my whole point in this is that they are very, very stable devices like diodes and transistors, and we use silicon. Now, if you're a guitar player, like I heard some people are, and I am as well, when I built my fuzz pedals, I used germanium. I didn't want any part of the silicon because the silicon sounded harsh. Part of the reason why 50s and 60s guitar pedals are so, those old vintage pedals are so in demand is because a lot of them use germanium components. So if you go play in the Royal Albert Hall one day and then you're in Germany in another little place another day, that device is going to respond to the difference in humidity and temperature in one room versus the temperature and humidity in another room. And so it's like you're always playing a slightly different instrument. And so, musicians love that variability and say, I can't wait to hook up my pedal and see what it sounds like in this place. And even as people come into the facility and the temperature changes because the amount of people that's there changes, that heat can sometimes change the component. So, I've read stories of people who use this older equipment that when they go to the sound check with nobody there, it sounds a certain way. And then by the time it's full of people and all that heat is in the building, the germanium transistor sounds a little bit different. Now, back to my smartphone example, if you're in the sub-zero temperatures of Alaska, you don't want your phone to stop working just because the temperature is too low. So you want something that's more stable, and that's why we use silicon in almost everything. Okay. You may see something like this on the quiz or the exam. Different things here that whether they're an insulator, conductor, semiconductor. So a plastic bag, air. Air is a good insulator too, and so we use air core for inductors. We use air core for capacitors if we want a dielectric or an insulator. And so you might say, well, how is air an insulator? Because I just had a storm last week and there was lightning and I saw it hit something. Okay, so I said a little bit earlier that an insulator could be broken down. So what you're seeing is there is so much voltage and so much power that it literally rips the air apart to have that lightning strike. Okay, that's why they're so dangerous, because the amount of energy required to break through that air insulator is unbelievable. Okay, so so very, very dangerous. But for the most part, air we use as an insulator. Okay. Now, water, I said earlier, it reduces the resistance typically, but it could also be a semiconductor. It also could be an insulator. It just depends on the state. Okay, water is used all the time in industry for boilers, to create power in a facility. They still use a lot of water pressure. So it just depends on the application. But for our purposes, water is bad. Water is a conductor. Okay. And especially if you add something like salt in there. You may have done the experiment in your chemistry class where you have salt water or potassium chloride salt water that will power a light bulb without making a connection, because the electricity will actually travel from particle to particle and actually make a connection inside the water. So water is very, very dangerous around electricity, and for the most part we consider it a conductor. Okay. Now, if it's in ice form, it's not gonna do the same thing. Okay. Semiconductors, again, silicon diodes, carbon film, that kind of stuff. Silicon diodes, germanium diodes, rectifier diodes, that kind of thing. Those are all semiconductors. And then good conductors are copper wire, steel auto body, battery acid, aluminum. Okay. Those are all atoms with at least with 1 to 3 electrons in that outer shell. Okay, and the most common obviously is copper wire. Okay. I'm not going to talk about the ions. I've always found that this just confuses students, especially if they don't have a chemistry background. That's where I did a lot of ion work, especially in organic. That was a nightmare, by the way. I had originally planned to measure in chemistry and double E. And after organic, I decided that probably wasn't something I wanted. I either needed to pick one or the other, and I decided to stay with electricity. So, okay. So here's a typical battery here, and this is how, when I say that there's electrons pooled on one side, this is what I mean. So point A here, it says, has fewer electrons than point B. So when you have a difference from like this has fewer electrons, this has considerably more electrons, you have what's called a voltage potential across there. Okay, but let's start with the charges first. So like charges repel. So if you have positive and positive or negative and negative, and then what did Paula Abdul tell us? Opposites attract, right? So if you have opposites, negative and positive, or positive and negative, they are an attractive force, whereas if you have two like charges, they are repellent forces. Okay. It says electrical energy sources separate the charges. Okay, so it's not like there's positive charge on one side and negative charge on the other, even though that's what your battery says. If you were to look at any AAA, AA battery, one's going to say positive, one's going to say negative. Okay, really what that means is one has a higher voltage potential than the other. That's all that means. Okay, so like you can see here, the negative end has a higher concentration of electrons. This has some electrons, this has way more electrons. And so the difference in that is 1.5 volts on a standard battery. Okay, and so if we wanted to look at the force that's generated between two charges, okay, we have this K. So this is an equation that you'll be asked a few questions on. And so notice that the d squared here, which is distance in meters, that is in the denominator. It's a squared term in the denominator, so you're going to get an exponential response, okay? So I always use the example of, because it's very, very similar in how it works, if you take a magnet, right, and if you have two magnets, and one has a north and a south end, the other has a north and a south end, what happens when you try to touch two norths or two souths? You know, that repellent force. It never actually lets you get, you know, because as this D becomes smaller and smaller, it makes this, you know, a gigantic force. Because, you know, when you're talking about, oh geez, if you're talking about millimeters or whatever, that small value is going to come back up to the top and get multiplied against all this, and you're going to have a huge force. So that's why you can't ever, you know, push I mean, I guess you could do it if you had, you know, two machines that just force the ends together. But if you try to do it by hand, it's almost impossible, because you're you know, as the distance gets closer and closer, you have an exponential amount of force that's trying to keep them apart. Same thing if you have a positive and a negative, right? If you try to make it to where they almost touch but don't, you can't do it, because the closer you get, that attractive force becomes exponentially stronger and stronger, and eventually it's just gonna grab it out of your hands. Okay, so that's the way I like to think about the force equation as well. All right, so we've got this d squared term in the denominator that makes the force exponentially larger if they're very, very close together. All right, and they follow this kind of a pattern here. So like charges repel, and opposites, like Paula Abdul said, opposites attract. Okay, and so this is a visual representation of those lines of force. Okay, so these are attractive forces, these are opposites, and so the path from one to the other is very, very nicely laid out, and life is good, right? But then you've got two that are like, and there's a clear line of division in the middle, right? You do not cross that line. We measure charge in what's called the Coulomb, so that's the first measurement unit that we're going to use. And a Coulomb is nothing more than somebody saying, okay, if I gather up 6.25 times 10 to the 18th electrons, that's a Coulomb. So it's just gathering up a bunch of electrons and calling it something, all right? Now, obviously, that's not a random number, okay? Obviously, when this was created, that's a very specific number of electrons, and so there's a reason why that was done, okay? So 1 Coulomb equals 6.25 times 10 to the 18th electrons. That's the first conversion that we're going to talk about, okay? Now, this explains what I was discussing with the battery back here, that you have an electric potential that exists because one side of a battery is, or you know, for that matter, one side of a component has a higher voltage potential than the other one, all right? So we have this new equation here that takes into account the charge, right? So charge is measured in coulombs, but we have the formula unit of Q for charge. Okay, so that's where that came from. So voltage is now equal to the work done per how much charge there is. Okay, so like we said, it's essentially the power to move electrons. So it says a potential difference of 1 volt will exist if 1 joule of energy is used to move 1 coulomb of charge from one point to a second point. Okay, so if 1 joule of charge can move 6.25 times 10 to the 18th electrons from one point to another point, that's 1 volt. Okay, so you may see a couple of plug and chug questions on this. Okay, using this equation here. So ultimately, you're going to either have joules or coulombs or volts here. And sometimes you'll see this written as W equals QV. That's just rearranging the problem here. Okay. So all of these are different variations of voltage here, right? So electromotive force, electrical potential used to move electrons. All right. And so, you know, today we use this. We use V equals I times R. If you were to look at textbooks from the 40s and the 50s for electrical engineers, they were all like this. E equals I times R. And there's a few times in the semester where I will refer to the voltage as E. But the E stood for electromotive force. Okay, and it was usually a script E. But eventually, you know, the newer textbooks have us use V equals I times R. But it's the same thing. Okay, potential difference, the difference in the amount of charge between two different points in a circuit. Voltage drop, the difference in the amount of electron energy between the two ends of a device. So I will reference these all the time, right? You know, what's the voltage drop across a resistor? The voltage before the resistor is 10 volts, and then after the resistor, it's 8 volts. So that voltage drop was 2 volts. Okay, and all of these are measured in voltages. There's not a whole lot to discuss on this, just the different points here. And most of the time, I'm going to be talking about voltage drops. Okay. I'm going to go over how to use the DMMs in a separate unique video, so I'm not going to go over these slides right here, okay? So let me go ahead and get into chapter 2 here in just a second. Let me go ahead and pull it up from our website. So that's essentially chapter 1. It's just setting up the foundations for so this is 1B. Let me see if this is getting too far into the woods here. Oh. Okay, I think that essentially covers all of the, because next time we're going to talk about sources and components. Okay, so again, this is a 3-hour ordeal today, and I didn't even have to get to I set all my camera up here, and I didn't even need to get to it today. So let me come back here to the comments, see if we have any questions. Okay, so I'll just say, because a couple of people said, hey, you know, I've got another class that's going on. I've got to be at work at, you know, a certain time. Not a problem. Not a problem. Let me type this out. Not a problem if you have to leave early and watch the rest on demand. Okay? Oh, he said, nice Mandelbrot background. Oh, thank you. I am obsessed with Fibonacci and fractals and all that kind of stuff. I find it fascinating. Oh yeah, Austin said, and how much of a problem being off a 1/16 of an inch in woodworking can be. Yeah, I have a picture of my very first table I built, and 2 of the corners are 90 degrees. And the other 2 add up to 180, but one's probably about 81 or 82 degrees, and the other one is more than 90, right? So about 98 degrees. So that's not, is that 100? Yeah, that's 180. So yeah, a 1/16 of an inch can be, you know, light years away. So Ethan says, what is valence? Is the outermost shell of an atom. And so the way we talked about conductors and insulators, conductors, insulators, and semiconductors, is that conductors have between 1 to 3 electrons, and they allow current to move very freely. If you have 4 or 5, it could be 3 to 5, but I typically say 4 to 5. that's a semiconductor, and 6 to 8 is typically an insulator. Okay, and that just it tells us whether or not something can pass free electrons easily. Okay. Matsuni says, isn't this directly linked with the Cavendish experiment? I'm not sure. I do not know. Okay, so Matt's saying, I did an experiment that compared rulers in my house after listening to a Dillahunty speech and found about a 16th error on a yardstick. Yeah, I mean, it was eye-opening to me because I thought, well, if you buy a tape measure, it's a tape measure, and who cares? You know, really the only thing you're buying is the protective cover around the steel or around the tape measure, and boy, that's not the case at all. You know, so you know, for my work that I do, if I start with a certain tape measure, I have to finish with it, because otherwise, if I use a different one, I could be off. You know, like we were talking about, just that 1/16 of an inch. So I don't see any other questions. Yeah, any place current can go that can shock is liquid and metal. Yeah, liquid, metal, any of that type of stuff is very, very bad for if you're trying to be safe in what you're doing. So, yeah, so not a problem if you have to leave early and watch on demand. Oh, okay. Maybe I need to. I'm just looking at. He said Kevin just discovered G, I think. Okay. Yeah, so maybe I need to go look at that. I may know about it already and just didn't know that's what it was called. And so another question here, do we need to do anything else until the next class? No, I mean, yes and no. You're not going to have an assignment due. You are going to have a lab that's going to be due the following week, but I'm going to release that on Wednesday, okay, because today was kind of a long class. We'll get to it on Tuesday. I'll just release 2 labs, not a big deal, okay? And I realize that some of you aren't going to get your lab equipment until next week anyway, so not a big deal, because you're going to need your DMM to measure the voltage, okay? If you just wanted to buy something, if you wanted to get ready otherwise, you need to have, I would say, at least 1, maybe 2 9-volt batteries, okay, brand new ones. And you'll also notice, I'm not going to give it all away, but you'll notice that when you buy a 9-volt battery, it's not exactly 9 volts, okay? It's a different value. When you buy a C battery or D battery, it's not 1.5 volts exactly. You're actually buying 1.64, 1.63. You know, they've got some different methods that they use where they can squeeze in just a little bit more so it looks like they last longer, okay? If you buy one from Harbor Freight, it's 1.60 on the money every time. I've never seen one that varies. So they use like the base amount, and that's it. Harbor Freight batteries, I should say, are good for kids stuff that runs out of batteries all the time, that they leave stuff on because they're so cheap. But, you know, you might spend a couple more dollars on a real. I say real. That's not the right term. For a new like Duracell or Energizer, you know, it's like maybe $5 or whatever. But buy one that's a little bit more. You don't have to if you don't want to. People used whatever they had in their homes, but make sure it's a new one so that you have at least that 9 volts. Okay. Oh, he says I just got my DMM from UPS and missed answering what we should do. So, like I said there, if you want to, I would go ahead and look at the PowerPoint for Chapter 2 so that you kind of know what I'm going to approach. And then I'm also going to be doing some board work. So it's not, you know, today was all PowerPoint. I don't like doing all PowerPoint because, you know, even though I'm explaining some of the things that are on the slides, I much prefer to do examples on the board, okay, and just try to do as many of them as possible. Over and over and over so you get the methods down. But we're not really to the point yet where we're going to do that kind of stuff. So I would read in your book, and I would try to do some of the homework problems out of Chapter 1. They are really straightforward. And prepare yourself for quiz over Chapter 1, which I will release on Wednesday. Okay? So what I'll probably do on Wednesday is release both Lab 1 and 2, and then also release Quiz 1 and 2. Now the quizzes, I'm not going to extend the dates on, but I may make I don't even know if I'm going to put a definite due date on Lab 1 and Lab 2 yet. I may wait until next week. I'm not sure. Okay, let's see how much of the equipment comes in here in the next week, and then we can go from there. Okay, so if there's no other questions, then you are all free to go. And if you're watching this on demand, remember that you need to comment and let me know that you have watched the video. Okay, so thank you everybody for showing up, and I will see you all at 1 o'clock in Zoom on Wednesday, and then it'll be a much quicker Zoom meeting then, and then we'll come straight over to YouTube and get started on the lecture. Okay, so I will see you all then. Take it easy.